Centrifugal pump. Today we would like to discuss about Euler head. So Euler head is the theoretical head that can be created by centrifugal pump. So in this topic, torque is defined as the angular momentum rate. And normally angular momentum is defined as mv and r. To calculate angular momentum rate, so we have rate here, so we use mass flow rate m dot instead of mass only. So to calculate the angular momentum rate, we are multiplying mass flow rate times tangent velocity and times radius. So we could say that angular momentum at inlet is m dot v world 1 and r1. And angular momentum at outlet is m dot mass flow rate v world 2 and r2, which is m dot here is the mass flow rate. And then we need to calculate the changes of angular momentum rate. So the torque here is the changes of angular momentum rate. So we deduct momentum rate at outlet minus momentum rate at inlet. So why we deduct 0.2 minus 1? Because this is a pump. Pump means a part that increase energy in the flow. So mean when water flow from the point 1 here to point number 2 here, the energy at point number 2 is is higher compared to energy in point number 1. That's why we deduct point 2 with number 1. So we substitute the value of m dot with rho AV or with rho Q. So we could write this equation into P rho Q V world 2 R2 minus V world 1 R1. And then we also could define that power is torque times rotational speed, T and omega. And from these terms, we could get that T is equal rho Q, V world 2 R2 minus V world 1 R1 omega. And then as I explained in previous lesson, the omega here is in radian per second. However, the velocity here, v world 1 here, will describe in meter per second. So we need to change the unit here, r omega here, into the linear units. So we know that U is equal to R omega, and U1 can be written equal to R1 omega and U2 equal R2 omega. And then we could simplify this one. We have R1 equal U1 over omega and R2 equal U2 over omega. And then we substitute in this term R1 and R2 here, and then the value of omega here can be cancelled out. So we could say that power is equal to rho Q V world 2 U2 minus V world 1 U1. And then, as we discussed in previous lesson, the general equation for power is rho GQH. Now we could equalize this term with this term. The value of H must be maximum to produce a maximum power. Assume that there are no energy losses in the system. Maximum power is an ideal condition. We could substitute H as HE. It is called as Euler head because there is no losses here. There is no energy losses, and the H is the maximum. So the Euler head here is actually the theoretical head of the pump. So we could write that P power equal to rho GQHE. The Euler head, the theoretical head, is equal to rho Q V world 2 U2 minus V world 1 U1. Then we could mention that Euler head here, HE, is equal to 1 over G, which is G is the gravity, 1 over G V1 U2 minus V1 U1. And Euler head, HE here is known as Euler head. The unit is in meter. So this is an ideal head produced by the impeller in pumping system. Ideal here means that there are no losses at all. This is the Euler head. As we mentioned previously, it is equal to 1 over G, V2 U2 minus V1 U1. And this is the ideal head of the pump. If we look to this equation, to have maximum value of Euler head here, we must make sure that world velocity V1 here mean V1 at the inlet is equal to 0. We cannot have U2 or U1 equal to 0 because U2 and U1 is the rotational speed, the linear rotational speed of the blade. So the only possibility to have maximum value of Euler head here is to reduce the value of V1. And V1 here is occur because of the turbulence that occur at the inlet. So means that if we could design our impeller blade at inlet very well, and we could design the inlet or the suction pipe, the eye design of the pump very well, we could reduce the possibility of whirl or turbulence occur at the inlet. So normally nowadays engineers are capable to design pump that do not have any turbulent velocity here. So means normally in our calculation we could assume that V world here is equal to 0. So what happens if V world equal to 0 means we have no component velocity of V world here. So and then the velocity triangle at the inlet will become like this. So at this moment we assume that V1 is equal to Vf1. That's why in my previous slide I show you the backward, the radial and the forward velocity triangle with the triangle of inlet without V1 here. So please make sure that you could draw a velocity triangle with and without the V1 here. However, it depends on the question. If the question asks you to calculate V1 here, so means the world velocity or the turbulent velocity is occur at that situation. If there are no the question didn't mention any condition, it is okay for you to assume that V1 or turbulent velocity is equal to 0.